So what we're doing now is we're doing similarity in triangles, getting back to triangles. And you can show that two triangles are similar when you know the relationships between two or three pairs of their corresponding parts. This first part is 2. You'll see the other examples, the theorems in a minute. But if you know two angles are congruent between two triangles, then you have angle-angle similarity. As you know, if you know two angles in a triangle, you know the third angle. And if you know that two angles are congruent within two triangles, between two triangles, then you know that the third angle is also going to be congruent, okay? So knowing that, then we have that all the angles are the same, and this is what we talked about earlier last unit, where if you have angle, 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 you don't have congruence, but as it turns out, you do have similarity, where you know that it's the same shape and just not the same size. Okay, let's stick with that for a minute. All right, so let's apply this idea. Are the two triangles similar? How do you know? Just a fun fact, this is not a similarity statement. We don't know that the vertices are lined up correctly. These are just two separately named triangles, okay? So if you did find that they were similar, you'd have to write the similarity statement by checking which vertices line up. Anyway, what do we need? We need that two pairs of angles congruent. That's what we need in order to do this. So let's see if we can prove that. For this first one, are the two triangles similar? Well, as you may be able to see, we have these two angles measuring 45. And although we don't know what these two measure, we do know that because they're vertical angles, they're congruent. And therefore, by angle, angle, we have angle, angle similarity. Okay? And so we can say triangle RSW, R 45 to S, the vertical angle to W, is similar to V, the 45-degree angle to S, the vertical angle to B. Okay, that's how you write it. What about this next one? These two triangles, are they similar? Well, as you can see, this angle right here and this angle right here both measure 70. So we have one angle congruent, but when we do the subtraction here, subtracting 30 plus 70 or 100 from 180, we find that this angle is 80. And this angle is 85, so they are not similar, okay? Try it with these got it problems, see how you do. So in the beginning, we said that you need two or three things, pieces of information. Angle, angle similarity is two pieces of information bit. These are the three pieces of information bit, okay? Side, angle, side similarity. It's not the same as side, angle, side congruence. So what do we have to have for the sides? Well, we have whatever corresponding sides need to have the same ratio. AB, which AB without the bar over it is talking not about the side itself, but about the measure of that side. So that measure, that number that represents that length, divided by that number measuring that side, that over that equals that over that, okay? If the sides are in proportion and the included angle, notice it's side, then angle, then side, the included angle is congruent, then we have the triangles similar, okay? We also have side, side, side similarity. If we can set up a ratio of sides that simplifies down the same ratio every time, then we have similarity between the triangles through side, side, side similarity. Okay, here's a proof of side, angle, side similarity based on angle, angle similarity. I'm not going to go through all this. It's a little bit complex, and you can pause this and read it as you like if you want to look closer at it. Now we've just learned about side, angle, side similarity and side, side, side similarity. This is problem 2A. There's going to be another example problem in just a moment. But are the triangles similar? If so, write similarity statements for the triangles. Fun fact here, the shortest side has to match with the shortest side. Middle length side matches with the middle length side. Longest side matches with the longest side. If that's not how it was, then you would never get get similarity. So that's how you know which to line up. Okay, so you can set up the shortest sides, the longest sides, the middle length sides, or the remaining sides, right? Um, and check the ratios, and they are proportional. So now you can then say, okay, how do I figure this out? Well, you can figure out what vertex lines up by saying, okay, that shortest side here and here, between the shortest side here and here, and let's say the longest side here and here, that's going to have the same vertex. So that S will map with Q, right? And you can see that S, I'm sorry, I said Q, but I meant X. S maps with X, right? That first letter. And you can keep doing that all the way around. What vertex is between the middle length side and the longest side, middle length side and the longest side, U and W. So U is going to map with W, etc. Okay. And this is side, side, side. We have all three sides similar, or in proportion rather. So we have side, side, side similarity. So are these triangles similar? If so, write a similarity statement. Well, we only have two pairs of sides. Guess what, though? We have a reflexive angle, so that's what we're going to have to deal with. How do we know what the length of that longer triangle side is? Well, you can do this if you like, which is to sketch it out and see those two triangles separately, but you can also just imagine with the segment addition postulate that that longest side KM on that triangle, the big triangle, is going to be 8 plus 2, or 10 there, right? And this is going to be 12 plus 3, or 15. So now we've got a length of 8 compared to a length of 10, and a length of 12 compared to a length of 15. And when you put those in proportion, you see that they simplify down to the same. So we have the sides are in proportion, and that reflexive angle is congruent, and therefore we have side angle side similarity through these triangles. And you can see how that L, well, they call it KLP like that, corresponds with KMN. Those vertices line up. See how you do with these got it problems. All right, this one we'll be doing a formal two-column proof. Given that side FG is congruent to side GH, making it an isosceles triangle, and side JK is congruent to side KL, also an isosceles triangle, and angle F being congruent to angle J, let's prove that these two triangles, FGH and triangle JKL, are similar, right? Let's take a look in our proof. We've got that the side lengths on the one triangle here are congruent, and the side lengths on this other triangle, those two sides are congruent. Okay, that's given. So what do we know from there? We know that those two triangles are isosceles. How do we know that? That's by definition of an isosceles triangle. If you have two sides congruent, you have an isosceles triangle. Okay. Now we've determined that they're isosceles triangles, so now we can determine that angle F is congruent to angle H, and angle J is congruent to angle L. How do we know that? Because, as you know, base angles of an isosceles triangle are congruent. Okay, so now we know that. And actually, if it helps, I can put the mark here now, like that. Okay, what do we got now? We got angle F is congruent to angle J. That was given information. And we've also then got that angle H is congruent to angle J because of the transitive property of congruence. We also know that angle H is congruent to angle L, also by the transitive property, meaning all of those base angles are congruent, right? So then we have that triangle FGH is similar to triangle JKL by the angle postulate. Yep. So try this got it problem. The first part is you're given that these lines are parallel, these sides are parallel, and use that to prove that triangle ABC is similar to triangle PBM. That's the first bit. Write your proof out. The next bit is to say, well, now we don't know that the lines are parallel. Suppose that the only thing we do know is that CA is proportional to PM the way that CB is proportional to MB. Okay, if you had that and you knew the other information that was there, do you have enough to prove it's similar and explain it? Okay, this is pretty great. Sometimes you're not able to measure something easily or directly using some measuring device, but you can use indirect measurement in order to find the measure. And here's the way that you essentially do it. You can see that, well, it says one method of indirect measurement is using the fact that light reflects off a mirror at the same angle at which it hits the mirror. So if this person is standing 5.5 feet tall at eye level, looking down at the mirror, and that they're looking to see exactly where the top of that cliff is, okay? And we're on level ground, so you have 90-degree angles here, and we know that these angles are the same because that's what it says up here. Light reflects off a mirror at the same angle which it hits the mirror. Then we have angle-angle congruence, and we have similar triangles. Okay, we're going to do that on the next slide as a problem. So again, here we have the setup. Before rock climbing, Darius wants to know how high he will climb up this cliff, which is X. I know these values are small. I'll tell you what they are. Okay. He places the mirror on the ground and walks backward until he can see the top of the cliff in the mirror. What is the height of the cliff? And again, notice that he adjusted his distance from there in order to be able to see exactly that top of the cliff. Okay. Well, first thing is, before solving for X, we need to verify that we're dealing with similar triangles. And as they say, triangle HTV, this right here, is similar to triangle JSV by angle-angle similarity, because angle T is congruent to angle S, they're 90-degree angles, and this angle HVT is congruent to this angle JVS, because we know that about mirrors, right? That you're gonna get the same angle there and there, okay? So then what do we get? Okay, since we have those triangles similar, we can say corresponding sides of similar triangles are proportional, and we set it up like that. And we have X for that height. So since we have X for that height, we can then cross product property and multiply, set them equal to each other and solve out, and you find that you get approximately 31.2, or the cliff is about 31 feet high. Neat. Okay, here's a got it problem for you. Why is it important that the ground be flat? To use the method that we just used. Explain it. See if you can explain it before we restart. That is your lesson on similar triangles. So give these lesson check problems a go. See how you do. I bet you could do these pretty quickly and just to verify what you know. Okay, try them, restart. Good luck.